This is my Unit 2 assignment. It's on Chapter 10, X-ray production. So the energy to produce X-rays themselves are electromagnetic waves that carry a much higher energy than visible light. The formula for kinetic energy is listed right here. Its kinetic energy equals 1/2 the mass times velocity squared, and the energy is proportional to mass, but it will change by the square of velocity. Next, we have interactions within the anode. This is a picture right here of the X-ray tube, and I have the anode circled. It's right here. So there are two possible outcomes that can occur when a projectile electron from the cathode end interacts with atoms in the anode, so coming from this end to this end. The first kind of interaction happens when it comes into contact with an orbital electron, and then the second kind is if it comes into contact with the nucleus. So first is bremsstrahlung. This is the kind where the emitted electron from the cathode end that went to the anode end leaves and then interacts with the nucleus. So it's commonly referred to as braking radiation, and that's a German word, and it's referred to as braking radiation because as soon as it comes into contact with this nucleus, it is deaccelerating and losing a lot of energy, and that energy that's lost is going to be emitted as an X-ray. So bremsstrahlung will account for majority of the X-ray beam. It is known as a heterogeneous or polyenergetic. It contributes to differential absorption, which provides subject contrast. The closer that a projectile electron will interact with this nucleus, the more energy is lost. So if this one interacts, like if an orbital electron came in from here and interacts right here with the nucleus, it wouldn't lose as much as if it got even closer to the nucleus. And it's more likely for the emitted electrons from the anode end to pass farther from the nucleus than to come into complete direct interaction with it. This is bremsstrahlung on a graph. It's this large area right here beneath the curve, circled as bremsstrahlung. Next is characteristic. It occurs from an interaction with an orbital electron. So just like how bremsstrahlung began, an electron is emitted from the cathode into the anode end, and from there it is projected. And when this interaction occurs, it's from that projectile electron hitting an orbital electron in a shell. It is within the atom's nature to reach a ground state where all electrons reside at the lowest possible shell position. So when this projectile electron happens, it's knocking an orbital electron out of its shell, and it's disrupting that electron's orbital electrons. So the atom will try to fill the inner shell vacancy by pulling a higher orbital electron down from its shell. And when the dropping of electron loses that potential energy, it emits characteristic radiation. So this kind of occurs from an interaction with an orbital electron. These are the binding energies for tungsten. K is 69, L is 12, M is 3, N is 1, and O is 0.1. You can see they're listed right here too on this image. It's actually possible to predict the energy that an X-ray will produce. You can determine it by the subtracted difference between the EV of the two shells involved. This is characteristic radiation on a graph. As we stated before, bremsstrahlung is this large portion beneath the curve, and these spikes here represent characteristic radiation. Even though they aren't as much as the bremsstrahlung, this is vast majority of the beam, and this isn't that much. They are high enough to make a real contribution to the final image. Excitation. Though bremsstrahlung and characteristic account for some of the X-ray beam, most of the energy is dissipated as forms of heat. Weak repulsion from projectile electrons at a greater distance raises the outer shell electrons to a slightly higher energy level without ejecting them from their atoms. To stabilize, they emit this energy as light and infrared light. So basically, there's too much build-up energy here, and they can't release these electrons, so they have to give off that energy as light. Lastly, I want to talk about the factors that affect the X-ray beam spectrum, because there is other contributions that go in besides just what an electron comes into contact with after exiting the anode. So there's 5 different things. There's your target material, your mass, your KVP, added filtration, and your generator type. So first, target material. If we have a material that has a higher atomic number, that means that more electrons are going to be compacted into a smaller space, which means that a collision is more likely to occur, which would yield more X-rays being produced. Next is mass, or milliampere seconds. It's the intensity of the beam, and it's directly proportional to the set mass, so doubling the mass will double the height of the beam spectrum. Next is added filtration, which removes low energy X-rays from the beam. Then we have KVP, which adds high energy X-rays, increases penetration or intensity, and increases the efficiency of X-ray production. Lastly is generator type. There's a couple different kinds. There's a single phase, what will show as a peak voltage, so it would be like a sharp point, a sharp triangle. And then we have three phase, which is known as a surge state, and it's more of like a constant rippling effect. More efficient generators will increase average KVP, therefore increasing beam intensity. However, subject contrast is reduced. So there's characteristic interactions and there's Bremsstrahlung interactions, and they do have a big effect on the X-rays that are produced. And as we saw in the graphs, Bremsstrahlung does take up a vast majority, but characteristic can affect that beam too, as well as these factors. So that is my video discussing chapter 10, X-ray production.